A 15,000-ton freight train traveling at 60 miles per hour needs to connect with another train. That's 30 million pounds of rolling steel approaching a stationary target. One small mechanical device, weighing maybe 80 pounds, handles the entire impact. No human intervention. No precise alignment required. The trains simply roll together. And somehow, this little piece of cast iron absorbs forces that could demolish a building. The connection happens in milliseconds. The coupling holds for thousands of miles. Today we're exploring how train couplers actually work. And after this video, you'll never hear that metallic clang at a railroad crossing without thinking about the engineering marvel that just happened. Let's talk scale. The modern freight trains that crisscross America's 140,000 miles of track are engineering marvels in themselves. These behemoths can stretch over 3 miles long, with more than 200 cars carrying everything from coal to containers. Each car weighs between 25 and 70 tons empty. And when fully loaded, a single car can weigh up to 286,000 pounds. That means a typical freight train can easily exceed 15,000 tons, or 30 million pounds. Now consider what happens when these massive forces meet. When coupling occurs, the impact forces can exceed 400,000 pounds. That's the equivalent of dropping a fully loaded semi-truck from a 5-story building. And what absorbs all that energy? A coupling device that weighs just 82 pounds. It's a scale disparity that defies intuition, an 82-pound mechanism controlling forces thousands of times greater than itself. Even more impressive is the speed and autonomy of the process. The entire coupling sequence happens automatically in under 2 seconds, with zero human input. No remote controls, no computers, just pure mechanical engineering. And this same basic design handles everything, from lightweight passenger cars to massive coal hoppers with equal reliability. The scale efficiency of the humble train coupler might be one of the most impressive engineering ratios in modern transportation. But this wasn't always the case. The history of train couplers is written in blood. In railroading's early days, from the 1830s through the 1880s, coupling cars was one of the deadliest jobs on Earth. Early railroads used what was called the link and pin coupler, a primitive system requiring workers to stand between moving railcars to guide a metal pin through a link. The process was brutally dangerous. A worker had to time his movements perfectly, placing his body between multi-ton cars coming together, often in darkness, rain, or snow. The statistics were grim. During the 1870s, it's estimated that over 38,000 railroad workers were killed or maimed while coupling or uncoupling cars. That's roughly 10 men every day losing fingers, hands, arms, or their lives. Railroad workers called the link and pin coupler the man killer. The average brakeman in the 1870s had a life expectancy of just 7 years after starting the job. The carnage was so routine that railroad companies simply factored worker deaths into their operational costs. Enter Eli Janney, a Confederate cavalry officer during the Civil War who later worked as a clerk in a dry goods store. Janney had witnessed the horror of coupling accidents firsthand. In 1873, he patented a revolutionary design, the automatic knuckle coupler. Janney's design mimicked 2 hands clasping each other with interlocking fingers that engaged automatically when cars came together. Most importantly, it eliminated the need for workers to stand between cars. But railroad companies, concerned about the cost of replacing equipment, resisted adopting the safer design. It took 20 more years and thousands more deaths before Congress finally passed the Railroad Safety Appliance Act of 1893, mandating automatic couplers on all trains. By 1900, railroad worker fatalities had dropped by 60%, one of the most dramatic workplace safety improvements in American industrial history. Today's modern couplers still use Janney's basic design, over 150 years after he sketched his first prototype. At its heart, the modern train coupling system consists of 4 fundamental systems working in perfect coordination. First is the mechanical connection, the cast steel knuckles that interlock like human hands shaking. Second is the pneumatic system, where air hoses connect automatically to synchronize the brake systems throughout the train. Third is the electrical connection, completing multiple circuits for signals and power. And finally, there's the energy absorption system that cushions the impact. What makes this entire process remarkable is that no external power is required for any of it. The entire coupling sequence is powered solely by the momentum of the moving train. The collision itself provides all the energy needed to operate every mechanical component, lock every connection, and engage every safety device. It's a masterclass in kinetic energy utilization. Let's dive deeper into how these components actually work. The knuckle coupler, the heart of the system, is a precisely engineered casting weighing about 80 pounds. Its shape isn't arbitrary. Every curve, angle, and surface is designed to guide the coupling process. As two couplers approach each other, their angled faces act like funnels, automatically centering and aligning the knuckles, even if the cars aren't perfectly aligned. The knuckle itself pivots on a pin and is spring-loaded to remain open until contact occurs. When the moving coupler strikes the stationary one, the impact rotates the knuckle closed. As it closes, a locking pin, called the lock block, drops by gravity into a notch, securing the connection. This gravity-operated locking mechanism is brilliantly simple. It requires no power, electronics, or human intervention, and it naturally defaults to the locked position for safety. Behind the coupler face is the draft gear, the unsung hero of the coupling system. This assembly of springs, friction plates, and hydraulic elements absorbs the massive impact forces during coupling. Modern draft gear can compress up to 3.25 inches under load, converting the train's kinetic energy into heat through controlled friction. This energy absorption prevents damage to cargo and cars, while protecting the entire train from shock loads. The draft gear also handles the constant push-pull forces as the train moves. When a locomotive pulls, the couplers experience tension, draft in railroad terminology. When braking or going downhill, the couplers experience compression, called buff forces. A well-designed draft gear system handles both extremes, dampening oscillations and preventing the accordion effect that would otherwise make train handling nearly impossible. But mechanical connection is only part of the story. Modern trains also couple their air brake systems automatically. This happens through devices called glad hands, spring-loaded connectors that seal against each other under pressure. As the cars come together, these pneumatic couplers align and create an airtight connection throughout the train's brake line. This allows the engineer to control the brakes on every car from the locomotive, essential for safe train operation. For passenger trains and some modern freight systems, electrical connections also complete during coupling. Multi-pin connectors automatically align and engage, allowing power, control signals, and data to flow throughout the train. This supports everything from passenger car lighting to advanced distributed power systems, where multiple locomotives throughout the train can be controlled by a single engineer. What's perhaps most impressive is the reliability of this system. The modern Type E coupler used on North American freight railroads has a failure rate approaching zero, despite connecting millions of railcars daily in all weather conditions. Each coupler is designed to last for decades, withstanding forces that would destroy most mechanical devices in minutes. Now let's walk through what actually happens during a coupling event. When an engineer needs to couple cars, they approach at a carefully controlled speed, typically 2 to 4 miles per hour maximum. Too slow, and the knuckles might not fully engage. Too fast, and the impact could damage equipment or shift cargo. As the moving car approaches the stationary one, the angled faces of the couplers guide them into alignment. At impact, several things happen in rapid succession. First, the draft gear begins absorbing energy, compressing several inches under the impact load. Simultaneously, the knuckle on the moving car rotates closed, interlocking with the stationary coupler. As it reaches the fully closed position, the lock block drops by gravity, securing the connection. The entire mechanical sequence takes less than a second. Once the mechanical connection is complete, air hoses between the cars swing together due to their design and positioning. Their glad hands connect, and as the engineer charges the brake line, these connections seat firmly and create an airtight seal. If the train has electrical connections, these also align and engage during the coupling process. Uncoupling is equally ingenious, though it does require human intervention. Each coupler has an uncoupling lever that extends to the side of the car, allowing a worker to stand safely away from the tracks while operating it. Pulling this lever lifts the lock block out of its seated position and rotates the knuckle open. The cars can then be separated by simply pulling one away from the other. Safety systems abound in this seemingly simple device. The lock block is designed to remain engaged even if the uncoupling lever is accidentally moved. Additional safety features prevent uncoupling during train movement. The coupler itself is designed to remain connected even if components wear or become damaged. This redundancy is why coupler failures are so extraordinarily rare despite the extreme forces involved. Maintenance requirements are surprisingly minimal given the stresses involved. Regular inspection of wear plates and pivot points is essential, as is monitoring the lock mechanism for proper operation. The draft gear requires periodic inspection for leaks or damage, but the basic cast steel knuckle itself rarely needs replacement unless it suffers an impact well beyond its design parameters. Many couplers remain in service for decades, connecting and disconnecting countless times without failure. When you consider the alternatives, the elegance of the knuckle coupler becomes even more apparent. Since Janney's original design, countless engineers have attempted to improve upon it. Various railroads worldwide use alternatives like the European Scharfenberg coupler or the Russian SA3 coupler. Yet for heavy freight service, nothing has surpassed the simple reliability of the knuckle coupler. Modern improvements have been evolutionary, not revolutionary, tweaking materials and tolerances rather than fundamentally changing the design. This speaks to a profound truth about great engineering. Sometimes, the simplest solution is the best solution. The knuckle coupler works because it embraces mechanical principles rather than fighting them. It uses gravity, not electronics. It harnesses the energy of collision instead of requiring external power. It aligns naturally rather than demanding precision. In an age of computerized complexity, the humble coupler reminds us that mechanical elegance still has its place. Every freight movement in America depends on this 150-year-old design. When you see a freight train rolling through your town, remember what you're witnessing. 200 cars, 200 couplers, each one operating with absolute reliability. No failures allowed, no room for error. The entire North American economy rides on these connections. That's the real beauty of railroad engineering. Not complexity, but absolute dependability. The same basic mechanism that saved thousands of lives in the 1890s continues to safely move billions of tons of freight every year. It's a testament to the power of good design and the lasting impact of solving a problem correctly the first time. Next time you hear that distinctive metallic clang at a railroad crossing, you'll know what it means. It's not just the sound of steel on steel. It's the sound of a century and a half of engineering excellence. It's the sound of physics, metallurgy, and mechanical design working in perfect harmony. It's the sound of the humble coupler, one of railroading's greatest innovations, doing its job once again. Have you ever wondered how those massive locomotives actually generate enough power to pull mile-long trains? I've already made a video about that. Check it out now.